Assalamualaikum students, it is the fourth lecture on the springs. In today's lecture, we will discuss different types of design conditions, design parameters for the springs. In the last lecture, we have also discussed different parameters like force calculation and of the spring, critical deflection, slenderness ratio, and the different conditions how to make a spring stable. Last lecture we discussed the different design parameters to avoid the different to avoid instability in the spring. So we discuss different type of parameter to avoid the instability in the spring. So we have in the last lecture we end with the geometrical condition like length and the diameter of the length and diameter of this spring, free length and overall diameter of the spring, and the end conditions like the supporting condition of the spring. In addition to these geometrical parameters, we have also the material parameters like elastic modulus and modulus of rigidity to control the different type of instability in the spring. So we have at the end with the relation like L naught is less than pi b over alpha and the material properties. So for absolute stability we have with these conditions, and for steel we have with the. So in the last lecture we concluded for stability of the spring we control the geometric parameters as well as material parameter. If we have we cannot control the geometric parameter, like we have some fixed length and some diameter that cannot be changed due to some constraint in the spacing. Some spacing constraint we have, and we cannot change the length and diameter of the spring, so we can maintain the stability still in this condition by changing the material parameter like elastic modulus and modulus of rigidity. If we have some constraint over the space and we have some specific length and diameter, and if by using this length and diameter we cannot maintain the stability, then we have other options like changing the material of the spring, and by changing the material you can get the proper stability of the system. Additional parameter alpha, so end condition also an important. So we can control the stability of the spring by changing the geometric parameters as well as end condition as well as the material properties. So using different type of material in the spring, we can control the stability if we have some restriction on the geometric parameter. These are the findings in the last lecture we have, and also we have discussed the different type of configuration of the spring. Slightly we have touched the topic, and I told you that it will we will discuss in detail in the vibration course. So the two type of configuration, series and parallel can be used for the different type of springs. So for parallel and as well as for series configuration, we have a different type of stability can this we have now in this slide we will discuss different type of material used in the spring. Spring is a very important machine element, so it in material science many of the research has been conducted on the use of the material for the springs. Mainly it is has a good fatigue life, and it have linear properties. It means when you use the spring, the load deflection curve should show a straight line. It should not deviate. So for maintaining these type of properties, you should have some material that remain in the elastic region, and proper stress strain curves you should have. For this purpose, different type of material has been suggested by and the different process in material science has been carried out, like different type of tempering and different type of other heat treatment process also has been carried out in the to achieve the good behavior of the spring, linear behavior of the spring, and greater life in the so these are the challenges in the material science, to have material that have linear properties, to have material that have long fatigue life, to have material that have high tensile strength, have a shear strength, have high shear strength. So these are the big challenges in material science. So we have achieved many good results for different type of spring. So first type of, in this slide you can see first type of hard drawn wire. This is the cheapest general purpose type spring, very general purpose type of spring that are very cheap. Just you have a hard drawn, in the drawn process you have make the wire, and but it has fewer lives, fewer accuracy, and not much deflection. It is very general purpose of spring that is used in the general application. Second type is oil tempered. Oil tempered is some way better spring than hard drawn wires. So this spring is made from ordinary hard drawn wire, or ordinary wire of the mild steel, or some high carbon steel, but in this as you seen, it has a carbon content 0.6 to 0.7, but main thing in this type of material you should have heat make is oil tempered. So why should have oil tempering? So oil tempering it will produce in proper properties of the spring. So for greater strength and uniformity of properties, it is heat treated, it is oil tempered. It is used for often for larger diameter of the spring wire, and it is again general purpose spring. Third type is the music wires. Music wire is a special type of wire that is made for the spring. It is exclusively made for the spring manufacturing, and it is has very much properties, just like high that they are tough, can absorb the high energy. One the property that I have discussed in the start of slide, like high tensile strength, high shear strength, and high fatigue life, and another property that is important, should tough. the material should absorb high energy, like you know, main area in the spring is the storing the energy. So material wire has the property of toughness. So music wire is made in keeping in mind that it is the very tough, so it can energy absorb more and more energy, and it is also have good fatigue properties, good high strength. So it is not cheap, but it is costly, and because it is specially manufactured for the spring manufacturing. Other type of spring is the chrome vanadium. Chrome vanadium, again, these are slightly expensive material, and these have especially properties of the spring. So these are used to make popular alloy spring steel. These have higher strength than plain carbon steel, and good fatigue strength, and also it is also very important for the shock and impact. For the springs that used for the absorbing the shock and impact and vibration properties, that should have chrome and vanadium. So these area have having chrome vanadium alloys that can absorb the high shock, high impact, have good fatigue lives. These are quite expensive, and these type of springs are very common for these specific application and shock and impact. And these are shock and impact are application in which springs are very much used, like in car shocks, car dampers, and other application in which shock and impact is involved. Last type is the chrome silicon. Chrome silicon is again an important category of the spring. It is also expensive alloy and used for the manufacturing of this type of spring. But again, it is very expensive alloy, and but it leads to good high stresses and long fatigue life, and accordingly it have a very much popular for using shock and vibration category of the area. So we generally have these type of springs, and all type of springs are basically depend upon the usage. And usage, if you have just a normal usage, like normal daily life, then we have just hard run wire or oil tempered wire, that are mostly cases we use. But for the very specific purposes, like some vibrational purposes and some shock purposes, we should have a spring that have much high strength, much properties of high fatigue, and important property of toughness. The important properties of toughness in the springs leads to the property of absorbing high shock and vibration. So high energy of shock and vibration will be absorbed by these type of springs, and it will lead to better properties, and accordingly we have this type of springs, and will can use in, but accordingly these are quite expensive, and due to expensive, these are so the application depends upon the area in this we are using. So we can categorize 2 or 3 type of application, like a general purpose application, in which we can apply some force and for this purpose we can use the different general type of spring. But for the application in which just not applying some force, but also the category of absorbing some energy, like some application of vibration and shock, and some application of absorbing some energy. So we have with the proper alloys like chromium, vanadium, and chrome silicon, and some more alloys has been not shown in this slide. Some have been invented, some alloys that named that is the according to these name has been assigned according to the application. These are called spring steels. These are basically specially for the purpose of high toughness and for spring properties, and these are mostly trade name, not material science name. Anyhow, these are the mostly most of the categories have been discussed in this slide, and at the end of slide we end with the different type of material that are mostly used in this category. Now, strength of spring materials. Strength of spring material is one more way it is represented by this formulation: S ultimate is equal to A over dm. In this formulation, S ultimate is the ultimate strength, and A is the another property that is provided for different type of spring materials, and d is the diameter via diameter, small d. M is against a property that is supplied for this, and that is available for different type of material. So if we draw a graph between these parameters, by drawing this graph on the log scale, if we draw strength versus y diameter, then we have a straight line if we draw on a log scale. By drawing this graph, we have A is the intercept and M is the slope. See this table. We have the properties A and M. This is the diameter of the. So by applying these properties in this formula, we will obtain the strength of the spring. Like what is A is in the kpsi, kilo psi inch power m. Different for it is given for different spring material, and it also showed that dia should be in the range in this, then it is applied. So dia for different range dia, these are parameters are available. So see the so it is for music wire, and this is for the hard drive wire, chrome vanadium wire, chrome silicon wire, and 302 stainless steel is the trade name. So different types of wires, and these are ASTM number, ASTM American Society of Testing Material. According to this standard, different material has been assigned different names. So these are the basically trade name. These are basically commercial name of the material. Like you can see music wire having a name of A228. So these are the material names. They are according to different standards. ASTM standard, American Society of Testing Material, nominate these type of material for different configuration of the material composition. So these music wire have exponent m 0.145. It is applicable in the diameter range 0.004 to 0.256 inches, and it has a value of 201. And in a similar way, for the diameter range 0.1 to 6.5 is in this range, and relative cost of the wire has been also been given in the table. Relative cost means when you compare these material when you compare different type materials, and the relative cost will be if it has a greater value, it means that will be costly material. Like this is the 2.6 is the for music wire, it is 2.6. It means it has some medium cost, and it is for one hard drawn one, as we have also discussed in the last lecture, that some type of material have cheaper, and some have expensive. So according to our requirement, we can use the material. So relative cost of material is for hard drawn wire, it is less. And in a similar way, as I have also told in the last lecture, that the material containing chrome and vanadium, that are highly cost material. So say chrome vanadium material has high cost 3.1. In a similar way, chrome silicon wire has 4.0. In a similar way, you can see different other type of wires. Phosphorus bronze wires have high cost, and you can see that it has a similar way high relative cost of 8. So in this way, we can calculate the strength of the spring in the different properties have been tabulated in standard tables. Now in this slide we will discuss estimating the torsional yield strength of the spring. Yield strength of the spring can be assumed to be 60 to 90% of the tensile strength. For spring, we can assume that the yield strength of the spring, yield strength mean you have the SY. Mostly in these cases, we have shear, we have torsional components. So shear yield strength can be taken as about 0.6 to 0.9, 60 to 90% of the ultimate tensile strength of that material. So SSY shear yield strength can be taken for 60 to 90%, and from the static failure theories, you should have detailed knowledge of the distortion static theory, static failure theory. I think you have studied in very much detail in the start of this course, or first course in the machine design, the static failure theories. According to static failure theories, the shear yield strength is equal to 0.577 of the yield strength. This relation you have concluded in the static failure theories. So distortion energy theory can be employed for this purpose, and according to distortion energy theory, the shear strength is the 0.577 of the yield strength of the material. So correlating these two correlation, we have SY yield strength in shear of the spring can be considered as 0.35 to 0.52 of the ultimate tensile strength. We can consider about the we can estimate the torsional yield strength of the spring 35% to 52% of the ultimate tensile strength. So we have these two figures 30 it can be ranged from 35% to 52%. What you can consider any figure, I mean depending upon the safety factor, how you can safely design the system. You can consider this from 35 to 52%. So for designing purpose, if you have ultimate tensile strength, you can take the shear yield strength for the spring ranging from 35% to 52%. Some more restrictions have been implemented from the stability conditions and from the experience of the spring, that spring index, what should be the value of the spring index. For most of the application, the spring index should be ranging from 4 to 12. These and preferred rate of active spring term should be from 3 to 15. These guidelines have been provided on the basis of long history of experience in the field of spring, and on the basis of formulation that has been discussed in the past slides, that C should be in the range of 4 to 12. C means spring index, that is the ratio of the diameters of the spring, and that is the geometric properties. So geometric properties of C should be in the range of 4 to 12, and the other property, the number of active turns should be from 3 to 15. For designing a good spring, we have these considerations, that C should be in the range of 4 to 12, and Na should be in the range of 3 to 15. Another property and that is important for the spring design. This important property is to limit the maximum force on the spring. As you know, when you apply the force on the spring, the graph between load and deflection is the straight line. It should be straight lined, and we should achieve a straight line for good if we have a good design. To achieve its straight line and uniform behavior during load deflection, then the application of force should be limited to 75% of the maximum force. It means what is the maximum force? The force you have calculated in the design of the spring to get the straight line linear behavior, that should be limited, that should be not applied to the 100%, but 75% of the force should be applied. It means we should apply a limit on the force. It means the force should be limited to the 75% of the maximum force applied. So we can calculate a factor. We can calculate a factor to establish the maximum force that is applied to the compression spring. The maximum operating force of the should be 78 to 7 by 8 of the force applied. So just define a factor. Fs is equal to 1 plus zeta into force maximum. So the 1 plus theta into 7 by 8 into Fs, and from these equation we can conclude that theta is equal to 1 by 7 or 0.143. It means theta should be greater than 0.15. When we maintain this value of theta, it should be greater than 0.15. It means you would have a better application of force to limit the maximum force. So theta should be greater equal 0.15. It means when you apply this value of zeta greater equal 0.15, you will achieve the force within the 75% range of the force that apply of the maximum force. So this limitation is an important limitation, so that you can obtain the better fatigue life of the spring. So students, it is the end of the lecture. We will continue from this slide in the next lecture. It is the I think fourth lecture of the course, and in this lecture we have discussed different design parameters, and from these design parameters we obtain the different most of the important parameter, and also discussed today the different type of material for the springs. And concluding this truth lecture, we will meet for the next lecture in the fifth lecture. So thank you.